Okay, so thanks again to everybody who came to this brief workshop. We hope you've enjoyed it so far. And our last talk will be given by Jurij Volcic, who's moving from Copenhagen to Drexel in the fall, I believe. So take it away. Thanks so much.
Thank you. Thanks for the organizers to inviting me to give this talk. I have to say I'm a little bit of an outlier to this community. So nevertheless, there's going to be rational stuff, and there's going to be as much combinatorics as they can get close to. And all of this is based on joint work with Igor and Gregor, who are in Ljubljana, and James, who's in Florida at the moment. So basically, there's going to be two main parts to this talk. So it's going to be a little bit more algebraic than the previous ones, I guess. So I'll spend some chunk of time on free algebra and free skew field, especially on the second one, whatever that means, and then go to a certain topic about free skew field. Namely, we would like to understand some kind of a invariant theory for it, and I'll try to show some examples, some results, and of course, along the talk, I'll try to kind of also show what is still open, and you'll see that many things are still open. There's actually lots of things to try to do. Now to start at the beginning, so this little case is going to be a field at the beginning, just normal field. Later, I'll switch to. I'll be lazy, go to algebraically close of characteristic 0. It's not clear if that's essential, but it really helps, at least with the proofs. I'm going to talk about polynomials and rational functions. So they are going to be in variable x1 to xn, which are going to be freely non-commuting variables. So here, freely means that, okay, not just that they don't commute, that there's people consider various non-commutative stuff that's more or less commutative. I really want them to be completely free of any polynomial relation, at least polynomial relation at the beginning. And then I can think of all words in these letters x1 to xn in these symbols. I can take all their linear combinations, define multiplication by concatenating these words and so on. And what do I get? I get the free algebra over the set x1 to xn. And I'm going to think of free algebra as algebra of non-commutative polynomials, NC polynomials. So I want to think of them a little bit as functions. Right? So here we have one example, because they really look like polynomials, right? The only thing is I can't reorder the letters. Okay, so that's of course a classical object, and I'll talk about another classical object that is a little bit less known, and the analogy is the following. So if you have commutative polynomials, you can take fractions and you get the field of rational functions. Can I do something similar with free algebra? Do I get some kind of a universal object that is closed under inverses and so on? And before I go into the construction, what this is, maybe just a little bit of a warning, right? So I mean, warning. Why all of this is somewhat pretty non-trivial compared to the commutative theory. So in general, one can talk about skew field of fractions. So now when I say skew field, I mean this skewness, maybe it gives a feeling that it has special structure. No, skew field just means division. It's just different communities use different words. So division ring, just a ring where every non-zero element is invertible. And now I would say that a skew field D is a skew field of fractions of some ring R if R is a subring of D, and D as a skew field is generated by R. Right? So I mean, calling this fractions, it should be legal, right? Because you don't have fractions, you can have nested inverses and so on. But at least that's kind of a sensible definition. And maybe the first thing that you observe that what can go wrong in non-commutative setting compared to commutative setting is that there do exist non-commutative rings that are domains in the sense that you don't have any zero divisors or whatnot, but you cannot embed them into a skew field. Right? That's kind of a immediately in the wrong direction from the commutative case, where you know that, oh, I can embed a ring in the field if known if there doesn't have zero divisors. And now, even if you can embed something into a skew field, you can do that in many different non-isomorphic ways. Even for the free algebra that happens. So the free algebra has infinitely many non-isomorphic fields of fractions, meaning that there are non-isomorphic fields that I can embed free algebra in, and they are generated by the image of the free algebra. They are non-isomorphic. So of course, when you see this, so the fact that you can have many fields of fractions of the free algebra, you can ask yourself, well, is one of them better than the others? Whatever that means. We'll see a little bit of what that should mean. And this leads us to the free skew field. So free skew field is gonna be the best, whatever, yeah, for me, the best field of fractions of free algebra. How am I gonna make it? I'll start kind of symbolically. So let me first just take this curly R to be the set of all syntactically valid, recursively built formal expressions built from variables and scalars and arithmetic operations. So what do I mean by that? Well, I start with variables, I start adding them, I start inverting them. I always kind of, what I mean by syntactically valid is that I want to put parentheses in a sensible way, so that parentheses are as they should be. But I really just build all possible things, right? So I get expressions like these ones, these three ones, right? And okay, we can see that yes, I have some nested inverses. And you also, if you're looking at the last one, right, and you think of this really happening in some division ring, right? And then you see, well, okay, let's say that x1 and x2 are non-zero, and then then x1 times x2 is invertible, but then the inverse is the same as x2 inverse times x1 inverse. And you see that all of this would simplify to 0 to the -1, right? So this sounds a little bit nonsensical, but at the moment I'm thinking even this kind of nonsensical expressions. Of course, I don't want to stick with them, so then I do the following, and this is a pretty old idea. It goes back to Amitsur in the late 60s. You fix some skew field D. I just want it to be big enough in the sense that if I look at the center of a skew field is the field itself. I want this big field to be infinite dimensional over the center. And now if I have an expression like that, I can start talking about what's the domain of the expression with respect to this skew field. Namely, this should be all the tuples of elements in the skew field that I can evaluate the expression on it so that it's well defined. What do I mean by that? Well, I define these expressions, I build them recursively, right? So you kind of start looking at the innermost building blocks. You say, oh, can I evaluate that? And so on, right? So for example, if I look at this first expression, what would be the domain? Well, it would be pairs of elements in D such that x1 is invertible, meaning non-zero, and x1 minus x2, x inverse x2 is again invertible. Right? So you can describe. So this would be the domain. The domain would be a subset of pairs of the elements in D. After you do that, some of the expressions are going to have empty domain. For example, this third expression that we have written up there, I throw those away. I just keep the ones that have non-empty domain, that are defined at least at some tuple of elements in D. And then I say, okay, now I'm going to identify some expressions. I'm going to say, well, two expressions that are defined at least somewhere. It turns out that then they actually are defined on some common point from D. And I'll say that, oh, they are equivalent if they evaluate, if they have the same evaluation on the intersection of their domains. Now one can check that it's an equivalence relation. So the only thing that transitivity kind of requires a little bit of thinking. But once you figure out that, okay, so you have equivalence relation, you take the equivalence classes, and that there's a natural relation of, that there's a natural operation, multiplication and addition, like how you would think it is, like adding expressions and so on. And it turns out that, okay, not just that's a ring, it's actually a skew field. And what's not as easy to see is that it's independent, the structure of this is independent of the choice of D. Okay. So this is going to be my field. Now, before I do anything more with it, it's very fair to say that this might not be very, I don't know, nice for everyone, right? I mean, if I ask you, oh, what's your favorite skew field that's infinite dimensional over the center, right? I mean, I don't know what's mine. I don't know that many, right? So maybe you would want a version of this definition that kind of avoids working with infinite dimensional skew fields.
Sorry, can I ask a question?
Sure.
About this result of Amitsur. So a field counts as a skew field, is that right?
Yes.
So can I take D to be, I mean, it feels to me like if I took D to be a field, there might be a lot of accidental equality.
It's a problem, right? Because a field, I mean, it's its own center, right? So it's one-dimensional over its center.
Ah, I see. So
right. So you want
okay. Thank you. Yeah.
You want a big one. So that's the issue, right? And it's a fair point, right? I mean, I would actually, I don't want to work with infinite dimensional. I mean, I would like to work with something over this base little field K that I have, right? And you can do that. So what are our favorite objects? Non-commutative objects, well, not infinite dimensional skew fields, but maybe matrices, right? And this is, you see that this is much younger idea. I'm actually sure that algebraists were already aware of that earlier, but this kind of maybe comes more from this functional theoretical point of view. So in 2012, Kalyuzhny, Verbovetsky, and Vinnikov did the following. So I'm gonna forget about and before that, let me just answer some chat. Yes. So the free algebra over two variables, it's infinite dimensional over K as a vector space. So as soon as you have free algebra over more than one generator, the center is going to be just K. Okay. And yeah, it's infinite dimensional. So what's the basis? The basis are simply all the words in letters X and Y. Okay, so what did Kalyuzhny, Verbovetsky, and Vinnikov did? Said, well, okay, now let's take all expressions, and now I'm going to start plugging in tuples of matrices. And again, I'm going to say the domain of an expression is all those tuples of matrices where R of X makes sense, where all the inverses were computable. And here the important thing is now which matrices or which size am I using? Well, I look at all matrices of all sizes. So here I have for any M, right? So for all sizes. Again, you throw away expressions that have empty domain. You just keep those that have non-empty domain. You again define equivalence relation. You say, well, two expressions should be equivalent if their evaluations agree. And again, you get a skew field the same as before. And the question here is, so I'm taking all tuples of quadratic of square matrices so that all the products make sense. Yeah.
I'm sorry, I don't understand the word any in the context of that result. Could you say more, please?
Any, every, Okay, so what do I want? So so this is really, okay. So it's the union over all m's of all tuples of n times n matrices X such that R of X is well defined.
I see, okay.
Okay. So I get the same skew field as before, it turns out. And this is what I call the free skew field of non-commutative rational functions. So I think of elements as functions, and I actually define them like that, right? I define them as equivalence classes of expressions that have the same evaluations wherever they agree on the intersections of their domains. We see that I already kind of got this in two different ways, either by evaluations on infinite dimensional. Someone doesn't like the symbol. Yeah, that symbol is, yeah, if you read all the books, it was hand drawn on each page separately. Otherwise, yeah, you do a little bit of shifting and whatnot with LaTeX. So the way how I define this, well, describe this skew field in different ways, it already gives a feeling that it's universal in some sense. I'm not gonna go precisely into details in what sense it's in universal. So Cohn developed all this theory. How do you need to define the category of division rings? What are the morphisms? La la la, and it's universal. And there's actually many more. There's a few more constructions of how to get this skew field. I just want to talk about one other construction that kind of doesn't talk about functions whatsoever, but just talks about somehow about the free algebra. And this is due to Cohn and Reutenauer. I mean, Cohn started with that, but then kind of this last form, the cleanest form is from '99. So if I have an affine matrix over the free algebra, so in other words, I could think of this as this is often also called matrix pencil. So it's an affine, meaning that it's a constant matrix plus a matrix, constant matrix times x1 plus so on. I'm gonna say matrix is hollow if it has a big zero block of size aj. So means that all these matrices a0 to an, these are scalar matrices. If they have a zero blocks of size ij, where I plus j is bigger than d, right? So how should you think of that? Think of it like that. So if you have a matrix, scalar matrix that has this big of a zero block, you know automatically that it needs to be singular. There's no way for this to be invertible. And now I'm going to say, okay, now on the other hand, I'll say that, okay, this kind of a affine matrix is full if I can't change bases on the left and right to get it into a hollow form. So full is kind of the opposite of hollow. Right? Full is if I can't, so this pre-multiplying with p, post-multiplying with q, that kind of corresponds to simultaneously changing bases of aj's. Okay, so being full means that it's not singular for obvious reasons. And it turns out that whatever is not singular for obvious reasons can be invertible. So what Cohn did is, it's somewhat interesting. He considered the following. He considered the triples of vectors C and B and full matrices A. And on these triples, you can define some equivalence relation based on hollowness and whatnot, and arithmetic operations. And what you get is, you again get the free skew field. The difference is that before I had to talk about some evaluations, either on matrices or evaluations on skew, on some other division things. Here, you can kind of describe everything by just block forms of these matrices. And what exactly this triple corresponds to? It corresponds to the rational function, non-commutative rational function inverse of A, and then multiplying with the row C and multiplying with the column B, right? So it's kind of like you're taking the entries of the inverse of a matrix. And this is what's usually called linear representation or realization of R. It's called linear representation because this matrix A is affine. So kind of what's the idea? Before I talked about rational expressions and they can have nested inverses. And here I have just one inverse, but I have an inverse of a block matrix instead of having many nested inverses. Okay. So maybe these are two flavors, two flavors of how to define this skew field. Both of them are useful. Sometimes you think of them as functions, sometimes you think of them in terms of these triples of full affine matrices and vectors. Here we have one example, something that we saw before, but I didn't go into detail. So these two rational expressions as functions, it turns out that they are the same, and they can be represented by the following linear representation, right? We see that this matrix here, it's really linear in x1 and x2, and here I have two constant vectors, right? So how you go back and forth between these presentations, it's if Schur complement inverting block matrices means anything to you, that's how I go back and forth. Maybe just a little bit of maybe before I go forward. So one thing that's kind of annoying with non-commutative rational functions is that even here, when you look at these first two expressions, right? Maybe it's not completely obvious why they represent the same function, right? You would need to do a little bit of manipulation to convince yourself that, oh, the first one gives you the same as the second one, right? And you can imagine that as soon as this gets a little bit more complicated, it's really hard to just look at it and say, oh, they give you the same or not. So that's why these linear representations can be much more convenient to figure out which expressions are the same, because it turns out that these linear representations are unique in certain sense.
Is there a canonical form for elements of the skew field?
In a sense, yeah. So when these triples here, you can represent one function in several ways with these triples. However, if you look at those triples where d is minimal with respect to your function, then it's actually unique up to basis change, up to just multiplying a from left and right with an invertible matrix. Right? So up to this canonical, just changing the base of these matrices a0 to an, it's then you have a unique representative. Yeah. Maybe just a little bit of where this came from, or some names that you might recognize, and who cares about that? This part of non-commutative algebra. So the determinants were very popular at some point, right? So Gelf and Dreytak are two prominent names. Automata theory, we already saw Schütz and Berger today, right? So he was one of the people very much involved in here. And then in later years, control theory. So non-commutative rational functions arise as transfer functions of certain linear systems. Computational complexity, and maybe the area where I come from is non-commutative real algebraic geometry and function theory. So we really like looking at free skew field as something of functions. So these are functions for us, and then you can talk about inequalities in matrix variables and so on. A fair question is, well, this rational functions seem much more complicated than polynomials. So why do we go from polynomials to rational functions? Sometimes it's really unavoidable, right? So if you think of, if you ever had to deal with any matrix inequalities like arising from control theory, even if they are polynomials, if you want to resolve them, you need to go rational. There's just no way around it. Especially when you look at certain aspects of non-commutative polynomials, they are also way too rigid. For example, I'm not going to talk about that, but you can define convexity for these functions. And it turns out that there's barely any convex non-commutative polynomials, so you can't get any rich theory. But when you consider convex non-commutative rational functions, you get a rich theory. You can build up optimization procedures and whatnot. And finally, sometimes you can get somewhat rich theory with polynomials, but rational functions just behave very, very differently. And I'll try to highlight this in the rest of the talk, which is now going to be slightly more combinatorial. And that's what I said at the beginning, that I'm going to talk about invariant theory. So from here on, I'm going to assume that the base field is the algebraically closed of characteristic 0 to make my life easier. I'm going to have a finite group linear with a linear action, with a representation. Of course, and this n here, if you remember, this n was the number of variables that I'm working with, right? So if I have a linear representation of G, that also gives me then a linear action of group G. both on free algebra and on the free skew field. And now, if I look at the elements that are fixed by this action, if I look within the polynomials, that's what I'm going to call non-commutative polynomial invariants for this section of G, and similarly non-commutative rational invariants for this section of G. And now, very basic question: can I say something about the structure of these invariant functions, invariant polynomials, invariant rational functions? We'll start with an example. I'll try to go. I mean, this is the simplest possible non-trivial example, right? I'm going to have S2 working on K2 just by swapping the coordinates, right? So I'm just going to have two variables, x1 and x2. I'm just going to call them x and y to simplify the matters. So what are the invariants, or what are polynomial or rational invariants? Well, those functions are such that r of xy is the same as r of yx. So here r is missing. And when it comes to polynomials, it's a pretty old result that polynomials in two variables that are symmetric under exchange of variables. This is a free algebra on an infinite set. This particular set, so x plus y, and then this infinite family of other polynomials, right? And this is, when you see that the first time, it's kind of interesting, right? This is a free algebra on infinite set. So these polynomials here, there's no relations. Right? This is different than in the commutative setting, where of course we know that the polynomial invariants are commutative polynomials in x plus y and x times y, right? But you don't have this in the non-commutative set. You get infinitely many independent generators. So that's pretty old. But then what you can notice is that when looking at these generators, and that's what Agler and Young did, they noticed that these generators and consequently all the polynomial invariants, they are actually rational in these three elements. Right? These three elements are the first three of these generators, because every next generator can be written as a rational monomial. Those guys, right? You can verify this formula, and then you can go a little bit further, and you can say, well, actually, these three, not just that all polynomial invariants are generated by these three, all rational invariants are generated by these three. And there's no rational relation whatsoever between these generators, meaning that the invariants are free skew field on three generators. And again, this is somewhat interesting when you compare that to the commutative setting, where you know that rational functions invariant under switching the variables, are isomorphic to rational functions in x plus y and x times y. So you have two generators, but here in the non-commutative setting, I have three generators. Okay, so this was essentially the simplest example. Is there any question about this example? No. Okay, let me then say a little bit like what can be generalized from here. On the polynomial side, this can be completely generalized. So it's an old theorem that says that, well, if you have a finite group linearly acting on free algebra, then the fixed points, so the invariant polynomials, always form a free algebra on an infinite set. Almost always, unless this action is kind of a trivial enough, right? So if I'm being a little bit not nice to polynomials, I would say it's kind of a very, very boring situation, right? I mean, the invariants are always free and they are infinitely generated, right? You always have this infinite set, right? So you can't really, I mean, see anything from the group happening inside here, right? Which is of course not completely true, because this is just really looking at the algebra structure. But if you can start thinking of grading, and you can start talking about Hilbert-Poincaré series and Galois correspondence and you can actually get a rich theory out of it. It's just that if I just look at this very basic thing, oh, what's the structure of this ring? Just the most basic structure, well, it's free algebra on the infinite set. They are all the same. On the other hand, we showed now that at least when you have a solvable group, the rational invariants, they are always finitely generated as a skew field. Okay. And here I can already say a few open questions. Well, what we certainly have no idea about is this solvability here of this G really essential or not. So we don't know if it goes bad if G is not solvable. Also, we know that okay, you have this finitely generatedness. We don't know if the generators are free or not. Or rather, we know in certain cases, and I'll talk a little bit about that in the last few minutes. But we certainly don't know if that's true for every solvable group. And we don't know even something weaker. So this is some kind of a Lurov-like problem. If I take a skew subfield of the free skew field, is it again free or not? Right. So in the commutative setting, that's true if you talk about subfields of rational functions in one variable or in two variables, and then it fails for more variables. But in the free setting, we actually don't know what happens. I would imagine the answer might be no, but you know, it's that kind of a question of oh well, every subgroup of a free group is free itself, right? So it's this kind of a this kind of a question. I mean, for groups, we know that that's the case, but we don't know here. So I'm not going to say anything about the first and the last open question because unfortunately, I don't have any good leads at the moment. Let me say something about the middle one. So do I know sometimes that this is a free skew field? Yes, sometimes you know that. So if you have a finite abelian group faithfully acting with a faithful representation, then the invariance is a free skew field on precisely that many generators, free generators. I'm actually going to give a proof of that because that's kind of a it's not, once you know what to do, it's not that hard. I mean, it's kind of a putting blocks together. So how do you, I mean, and especially it's kind of going to explain where this number of generators comes from. Since I have a finite abelian group and I have characteristic 0 algebraically closed field, I can always diagonalize the action, right? So I can do linear change of coordinates, and then I can think of having diagonal action, meaning that the G works well, acts on variables just by scaling, right? So the scaling is then just given back character of the group of G. And then if I look at all the non-commutative words, that's the free monoid over x1 to xn, I embed it into free group on n elements. And then from this action, what do I get? Well, I get a homomorphism from the free group onto the character group. Okay, now, and it's subjective because the action was faithful to start with. Okay, so now I'm dealing with free group here, right? And here we have this nice theorem, old theorem, Nielsen-Schreier theorem, that tells me that, well, subgroups of the free group are free itself, right? So the kernel of this homomorphism is free. And even more, because this is homomorphism into a finite group, I actually know how many generators do I need for this kernel, and it's precisely this number here, this size of G times n minus 1. Then the next thing that you need is that, well, okay, now I take this kernel, right? These are invariants, no, not all invariants, but if I generate a subfield with them, it turns out this subfield is free, right? There are no rational relations between those generators, and that comes from Jacques Levin proved that. So it's really ring theory, division ring theory. And then finally, the last step that you need is that in this case, we can actually prove using linear representations that I mentioned before that, oh, the rational invariants are generated by polynomial invariants. And now all polynomial invariants are kind of captured by this kernel n, so that's why if I understand the kernel n well, I understand all rational invariants. So this, putting all of this together, yeah, so in this case, we know exactly how many generators do we have, and that they are free. Then you say, well, how further can I go from this abelian case, right? I mean, can I go now to some non-abelian groups? And there's a somewhat naive idea, and it actually works somehow. I mean, you could try doing the following. You say, well, okay, I have non-abelian group G now, but I can find, let's say that I can find some non-trivial normal abelian subgroup N. I know how to find N invariants. So that's the previous theorem. I know that they are N invariants. They're free on finitely many generators. And now the quotient group acts on this N invariants. If this action is still linear, then we kind of reduce the problem to this quotient, right? Because the invariants for the quotient acting on N invariants, well, that's just the original invariants for G, right? So if I can do something like that, if I can find a non-trivial normal abelian subgroup in this item 4, so the action is still linear, I reduced the question from G invariants to G mod N. And you can then kind of try to see, okay, can I somehow reasonably describe this kind of this class of representations? You can, and we call these representations complete, but the definition is so technical, I'm rather not going to write it down. So let me rather say, let me give you a specialized definition. And instead of defining a property of representations, let me define a property of a group. So I'm going to say what it means for a group to be unramified over a normal abelian subgroup. It means that if I take any irreducible representation of G, then the restriction of G to N is either trivial or split into distinct irreducible representation of them. And then I recursively define that a group is totally unramified if it's either abelian, or I can find some non-trivial normal abelian subgroup N such that G is unramified over N in the first sense, and this quotient is again totally unramified. Now this definition, what do I like about it? It's something that you can kind of check, right? I mean, you open gap, you get out all the you can find, using gap, you can find the normal abelian subgroups, you can find all the irreducible representations, you write a little bit of a script, and you have a program to check if your group is totally unramified or not. The whole point of this definition is that being totally unramified means that the left regular representation of this group is nice enough for our purpose. And just to give a feeling what kind of groups fit this, this setting, well, by definition, all abelian groups, metacyclic group, diagonal group, semi-direct products of abelian ones, for example, also S4 fits this framework. And the smallest non-example is this one of size 24. And what's the main theorem is that those nice representations that I did not yet define, that I didn't define, so it's kind of a pointless, but nevertheless, for certain nice representations, we know how to show that the invariant field is free on finitely many generators, on that many generators. In particular, that applies to all these totally unramified groups acting on themselves. So all this abelian metacyclic diagonal and so on. You always get this number of generators. And Gregor, one of the co-authors, actually extended this a little bit, also got some cohomological interpretation and whatnot. So he really perfected this technique as far as it gets. I'm going to skip one example that doesn't fit this, but let me just before I wrap up, just some open question where we kind of want to go further on. Is symmetric groups, right? We kind of want to understand symmetric non-commutative rational functions. So that just means that if I have a rational function on n in n variables, I want to understand those that are just invariant under permuting the variables. Now for n equals 2, I already did that. I got 3 generators. For n equals 3 and 4, you can also show using the result from before. It turns out that these are also free on 13 generators and on 73 generators. And now, of course, the question is what happens afterwards, right? So n equals 5, definitely I can't use the same machinery as before, because before this definition here, unramified, actually, if you look at this and think about it, it means that in particular G is solvable, right? And if you look at this previous theorem that I had, it also talks about solvable groups. So that's why I really, with these techniques, I can't really go all the way to N5 or higher. But on the other hand, I see here some pattern, right? So I mean, I would really like to understand what happens with this symmetric non-commutative rational functions if they are still free on finitely many generators. But we don't know. So maybe some to remember is that the free skew field, the universal division ring, in some sense, you can think of it in two ways. You can think of them in terms of linear representations, or you can think of them in terms of functions. I don't like, when it comes to invariant theory, I don't like polynomials because the invariants are never finitely generated. On the other hand, rational invariants are always finitely generated when you work with solvable groups. And if it's a nice group, you actually know that it's free, right? So that you can get free generators. But there's lots of things that we don't know. So again, this question is every subfield of a free skew field free itself. So you see in the commutative setting, when you ask yourself, is a subfield of rational functions again a rational field of a rational field? The first counterexamples came from invariant theory. That's why actually we were looking at this invariance, right? We kind of hope that by looking at some invariants for certain groups, we're going to be able also to see that, oh, we get something that's not free, but we didn't manage to do it. Okay, so and finally, yeah, what's the structure of symmetric non-commutative rational functions? This should be kind of a natural. They might have some very nice combinatorial description. It's just that from our proof so far, you can't really see any of them. Okay, thank you.
Thank you, Yuri.
Thanks, Yuri.
Yeah, I see the chat is mostly discussing about the symbols. I don't know, you probably share my misgivings about the crossed out parentheses. So
I mean, yeah, I think if you go to any of my archive papers and you look in the source file, you of course feel free to copy the code out how to get this parenthesis. Yeah, I think we always use the same. Probably now for 10 years we're using the same notation.
Yeah, thanks a lot for the talk, Yuri. So as I told, I could not really find a discussant for this because this is a little bit, at this point, this is a niche topic, but I think it will be mainstream in something like 5 years in combinatorics because of the quasi-determinants, also because of things like non-commutative birational remotion, non-commutative marked surfaces and cluster algebras, which is so far a fledgling field, but people are working towards it. Basically, anything you can do commutatively, you can at least ask whether it works non-commutatively, and in some cases, those questions have positive answers. So this theory that you showed for us combinatorialists, it's answering questions like, if you're proving an identity between two non-commutative polynomials, is it okay to assume that certain things are invertible, or is it not okay? Is it restrictive? The free skew field, at least partially, would answer this question. So I think this is all more important than it even sounds like if you're not an algebraist.
Mm-hmm.
I'm wondering to what extent has this been embodied in code that people could just use without necessarily understanding the innards?
So, how much is this encoded? So yes, we do. So there's a let me write this. There's a package written for Mathematica. It's still developing, but I mean it has. So it's kind of people from control theory were the first one that actually wanted to, actually want to do some down-to-earth calculations with NC-rational functions and how to automatically get these linearizations and how to get minimal ones and la la la. So this has been encoded in. So if you're okay with using Mathematica, there's a package for that.
So no one's done it in Sage as far as you know.
Not in Sage as far as I know.
But Jim,
adding to Jim's question, are these questions algorithmically decidable? Like, is there a procedure to, for your question about like n greater than or equal to 5, could I even come up with a way to list all the invariants maybe up to a given degree or something, or is that's not even known necessarily?
You mean with polynomials invariants? With polynomial invariants, it might
the rational function, or the ones that are finally generated, right?
Oh, I see. Okay. So definitely for these ones here, for let's say for the abelian ones, or for example for this general theorem that it's cheating because it didn't really define complete representations. Here you can actually there's a procedure for getting the generators explicitly. Yeah, and I would imagine I think if I go looking back in the proof of the solvable case where you don't have freeness, but at least you have finitely generatedness. In this case also, yes, you could write them down. Yeah.
But in the cases, I guess, where you're not sure yet whether it is even finitely generated, then.
Yeah. So it's not, and sometimes I'm also going to say, this, of course, the generators are not unique, right? And that's sometimes that's an annoying problem. And let me then show this example that I didn't because lack of time, but maybe I'll show a little bit how quickly annoying things become with choosing generators. Simple case, the ideal group D4 acting on two variables. So if I think of D4 as a cross product, semi-direct product of Z4 and Z2, right? So the Z2 part switches the variables, and if I think here as the field being complex numbers, then the first one multiplies by imaginary unit and minus imaginary unit. Now this group, it's a nice group in that sense, but this representation is not nice in the sense that I mentioned before. Nevertheless, you say, okay, I'll start computing this invariant, and you say, okay, I'll first look at this normal subgroup Z4 inside and compute this invariance for Z4. I'll do that because I know that these ones are nice. These ones I have an algorithm how to get them, and you get these 5 generators, right? So these are all invariants for the action of A. And now you think about, well, what's happening with the quotient? So quotient is just Z2. Okay, that's simple enough. Proof. How does it act on these generators for these invariants? Well, it acts nicely on the first 4, right? Because it just switches. So Z2 is this action of B, switching X and Y, right? It just exchanges Z1 and Z2. It exchanges Z3 and Z4, and then with Z5, it does something annoying, right? I mean, it sends X4 to Y4, and I don't see Y4 in my group of generators, right? So that's annoying. And then you kind of say, okay, but I can observe that I can replace this last generator by something else. I replace it by this Z5 prime. Now, this Z5 prime, you see that Z1 to Z4 and Z5 prime generate the same thing as with Z5 at the beginning. It's just that this Z5 prime, when you simplify it, you see that this quotient group acts nicely on it, right? It just sends Z5 to minus Z5. So what did I do now? I linearized my action somehow by doing some smart change of coordinates, rational change of coordinates. And now, okay, so then I can compute those invariants. And I again get that, oh, it's a free on that and that many generators. However, the problem was that really this getting Z5 prime was really guessing, right? I don't have a good reason why I figured that out. Right? So that's what I wanted to say, that I mean, in this case, in whatever this theorem is, here you have, you can do this algorithmically. Otherwise, you can get quickly to some relatively simple examples that you can, well, you can resolve, but you don't, I mean, you don't really have a good recipe.
Okay, any further questions?
Dari, I have one quick question.
Yeah.
So this is probably obvious to everybody, but on when you were computing the invariants under the action of the symmetric group of this, yeah, maybe your last slide or.
Oh, I see. Okay, there might not be anything too much obvious, but please go on.
I was just going to say that those numbers are the numbers of ordered partitions. So just that very small comment.
Okay, that's a fair comment. Yeah. So I mean, since I don't work in combinatorics, I actually didn't know that. I was checking in the online encyclopedia of sequences, and this sequence was not inside, so I didn't know where it comes from. So you're saying that this is the number of ordered partitions?
Oh yes, but it must be on the encyclopedia. So I don't know why it's not showing to you.
So just the faces of the permutahedron, is that what you're?
That's right. Yes.
You can try putting these numbers in 1, 3, 13, 73, and whatnot in there, and it says that, oh, there's no.
No. It is A000262. I mean, there are other results, but this 4, 1 through 73, in particular, agree with that sequence. Yeah. Anyway, who knows if that's the answer, but maybe at least you have a candidate for the next term.
No, but that's weird. I didn't plug in the first one. I didn't put the first 2 ones in, but Okay, that's a great point. Okay, excellent.
All right.
Yeah. So that's what I would hope for here, right? I mean, it's such a canonical natural action, right? I mean, there should be other ways of explaining these numbers than what we did with using the abelian case and then stretching as much as we could, right? There should be a better reason for treating symmetric groups.